Let's talk about some acid-base reactions. So acids, and we're going to talk about the definition of those in just a moment. They can either be strong or weak. And if they're strong, that means they were strong electrolytes. And you need to memorize what strong acids are. Hydrochloric acid, hydrobromic acid, hydroiodic acid, nitric, chloric, perchloric, and sulfuric acid. 7 strong acids. You also need to memorize these strong bases. They're basically the 1A and 2A hydroxides, the alkali metal hydroxides and the alkaline earth hydroxides. So the 1A hydroxides, lithium, sodium, potassium, rubidium, cesium hydroxide, and then the 2A hydroxides of calcium hydroxide, strontium hydroxide, and barium hydroxide. Memorize those. So let's define acids and bases. Historically, the first definition of acids and bases that came along are the Arrhenius definitions. An Arrhenius acid is one that ionizes in water to produce H plus ion. So hydrogen chloride gas, dissolve in water, dissolves and dissociates to make H plus aqueous plus chloride ion that's aqueous, an Arrhenius acid. An Arrhenius base is a substance that dissociates in water to produce hydroxide ion, OH minus. So go back to that previous list, sodium hydroxide, we said it's a base. Put it in the water, dissolves and dissociates to make sodium ion and hydroxide ion. Well, who was Arrhenius? Arrhenius also liked bow ties, and hooray for that. He won the 1903 Nobel Prize in chemistry for his advancement of chemistry by his electrolytic theory of dissociation. So that's Svante Arrhenius, a Swedish chemist who wore bow ties, who gave us these definitions. There's another way of defining acids and bases. If you'll notice, the Arrhenius definition talks about what happens in water. What if water is not the solvent? In organic chemistry, this following definition will become a big help because we're not in water. But we can use it also in water. It becomes a help also. Sometimes we can see some things we wouldn't see otherwise. So Bronsted acid is a proton donor. Proton donor. Let's take a hydrogen atom. Proton plus electron. Make it an H plus. You've taken away the electron. What have you got left? A proton, H plus. So hydrochloric acid, how is it a Bronsted acid? Hydrogen chloride gas, dissolve it in water, makes H plus, a proton, plus Cl minus. Bronsted acid. Bronsted base is a proton acceptor. So let's look at the ammonia for a moment, NH3. Now, if you're looking at ammonia, you scratch your head, it's going to be a base. Well, how's it going to be a base? If you look back at Arrhenius, it says it produces OH minus in water. And he does. And we'll see that in a moment. But if you just look at NH3, you go, where's the OH minus? You might even think he's an acid because he's got H's in it. He's got hydrogens in it. So let's see how we can describe ammonia as being a Bronsted base. So ammonia gas is actually gas at room temperature and pressure. You can dissolve it in water. It dissolves very easily because they can hydrogen bond with one another. What happens is that you can think of that water as dissociated. That water breaks apart that H2O to make H plus and OH minus. And so as it makes the OH minus, there's the base. Where does the H plus go? It goes to the ammonia, the NH3, to make ammonium NH4 plus. And so, yes, he's by Arrhenius, he produces OH minus, but now what he's done, that ammonia has accepted a proton from the water to make ammonium. And so that is another way of seeing how that compound acts as a base, even though looking at its formula, you might not guess that ahead of time. And so there's a picture of this. There's that trigonal pyramidal ammonia molecule that's aqueous reacting with H2O, that bent order molecule. It's in equilibrium because it's a weak base. Doesn't go to completion, just a very small percentage of it does. The ammonia picks up a hydrogen, So it goes from trigonal pyramidal to being tetrahedral, ammonium, NH4 plus, and the hydroxide ions left over. So in these definitions, remember, a proton refers to a hydrogen atom that's lost its electron. So it's known as a hydrogen ion. So there's Arrhenius definition that's good for water. There's Bronsted that's good for water or any other solvent. There's a third definition that's called Lewis acids and bases. We're not going to talk about it in this course. Chem 112, you'll do that. So what happens when you take an acid and base in your reactant? It's a type of reaction that we know as a neutralization reaction. And so the products of a neutralization reaction are water and a salt. Now, don't think of salt as simply being NaCl, sodium chloride. A salt is any ionic compound. That's a product of an acid-base reaction. So using examples that we've been using previously, hydrochloric acid, aqueous, plus sodium hydroxide, that's a base. Strong acid plus strong base, it's going to make water, H2O, that's a liquid, plus NaCl, aqueous, sodium chloride, that's a salt. So that's the molecular equation for the strong acid-base reaction, where we've written everything out as compounds. Could have also written the ionic equation, where everything that's AQ, we break apart into its constituent ions. So HCl aqueous becomes H plus Cl minus. Sodium hydroxide aqueous becomes Na plus OH minus. Reacts to make water, still a liquid in its molecular form. And then sodium chloride as aqueous becomes Na plus aqueous plus chloride ion aqueous. So we got the molecular equation, and then we got the ionic equation. And from that, we could come up with the net ionic equation. It only shows what changes from one side to the other. So we cancel out the spectator ions. What's present on both sides? Sodium ion is present on both sides, so they'll cancel out. Chloride ion is present on both sides. They cancel out. So what's going to be left? H plus and OH minus. The proton plus a hydroxide ion makes liquid water. That's your net ionic equation for a strong acid-base reaction. Thanks for listening.